The study of the electric dipole field integrates mathematical theory with computational dynamics to explore how forces and energy behave in a unique physical environment. The investigation begins by mapping the scalar potential, which serves to establish a detailed energy topography. This landscape is fundamental to the study as it dictates the electrostatic interactions that any charged particle will experience within the field. To complement this, a visualization of the vector potential is used to confirm the solenoidal nature of the field, providing a clearer understanding of its structural flow and directional properties. A critical component of this analysis involves the numerical verification of energy conservation. By demonstrating that the total energy, the sum of a particle's motion and its potential energy, remains constant, the study provides empirical proof of the field's conservative properties. This characterization is further refined through Helmholtz decomposition, a mathematical method used to verify the field's essential qualities. The culmination of this research is the simulation of dynamical particle trajectories. These simulations reveal that because the force exerted by a dipole is based on the inverse cube of the distance and is highly dependent on the specific angle of the particle, it creates complex, non-central orbital paths. These intricate movements are a defining feature that distinguishes dipole interactions from simpler central force laws, such as those found in standard gravity or basic point charge models.